my name's Melia, and I'm the head of marketing for Citrine Informatics. I have a background in materials, a degree in material science from the University of Cambridge. But when I was at university, data science wasn't really a thing, and AI wasn't discussed or used. So I think I'm in a good position to help everyone understand materials and chemicals informatics from a really simple point of view. So we're going to do an introduction. We'll first briefly go over who Citrine Informatics are, how AI for materials and chemicals is providing value to companies already. Then we'll get into the nitty-gritty. So how much data do you need? What type of data? What does the AI workflow look like? What are the different steps? Then we'll look at how it reduces the number of experiments that you need to do to hit your target properties. And we will finish off by demonstrating how easy it is to use and the fact that you don't need to be a coder or a data scientist. So Citrine was founded back in 2013. And what we do is provide AI software as a service in a web browser. It gets used by chemical companies, consumer goods companies, people who do packaging, anything where chemistry is important. And in these areas, it's usually with small data sets. So we've specialized in working with small data sets. If we think about materials and chemical development, we've got all sorts of levers that we can pull. We can change the processing parameters, we can add a new ingredient in, etc. All of those different options create a huge design space, one where we can't possibly test every option. Testing is expensive, it takes time, you have to make the sample, you have to use proprietary equipment most of the time. So testing everything, not an option. So what AI does is it helps you to explore this space systematically in a way that helps you find the best solution quicker. And I was actually on a call with a scientist from one of our customers when he said that when he was being trained, you're always looking at better, faster, cheaper. But he was told, you can't really get all three of those. Whereas now he was excited because he could try and get all three. He can look to optimize more parameters and do that more quickly. So some of our customers are on the right there. You can see that it's a variety of customers from startups to multinational organizations. And they trust us to stay cutting edge in terms of materials informatics. They trust us to keep their IP safe and not share it with any of our other customers, and we don't use it to train our models. And they trust us to guide them on their AI journey because we've been doing this since 2013. We've learned a lot along the way. So how can informatics help? So first and foremost, it can look at the formulation that you're using and help you to meet property targets with 50 to 80% fewer experiments. So that gives you agility. It gives you the ability to change things quickly. It also helps you to optimize processes simultaneously. So you can look at reducing energy use, reducing carbon footprint, etc. It can also be used to figure out how to produce something in another country with raw materials from that country. And lastly, it really helps in customer relationships. If a customer is coming to you and wanting change or submitting a request for proposal, they want a sophisticated answer back about what you can do for them, in what time frame, and what's realistic. And the quicker that you can help answer those questions, the better. So you can also use the platform to show how your product impacts the customer's product. For example, our customers who are specialty chemical manufacturers use it in formulations like paint formulations, for example, to show how their product impacts the properties of their customer's product and therefore to get a higher margin. So let's look at 4 specific examples. This is The first one, a major producer of thermoplastic resins. So they wanted to start using bio-based feedstocks and replacing fossil fuel feedstocks. They managed to do that, replace 90% of those, and they did it in 50% of the planned time for that project. Another company was focused on greenhouse gas reduction. They were looking at creating cellulosic esters, so a product where, again, with a bio feedstock. And they also looked at, how they can recycle copolymers as well. And they were able to reduce greenhouse gases by 20 to 50%. The third example here is a medical device manufacturer. They were creating a medical clamp made out of plastic. And again, they were able to optimize not just the plastic itself that was used, but also in production costs were optimized as well. So they were able to reduce carbon footprint, but also reduce product cost and development time by 50 to 60%. And then the last one is a polypropylene manufacturer. They do a automotive grade polypropylene used in cars. Obviously, in any form of transport, weight is an issue. So they wanted to reduce the density of the polypropylene while maintaining the mechanical properties. And they were able to reduce the density by 4%. And they estimate that that will give them an extra $50 million in revenue over the next 4 years. So we can see that materials informatics is working and is being used across many different companies. So let's now look at how do you get started. Let's go back to the basics. And oftentimes people worry about data, and it really isn't the thing to worry about as much as you perhaps think. So the way that we do AI with materials and chemicals, we know that you're going to have small data sets. This is not the same as ChatGPT, where you have billions of data points. These are physical experiments, and this chart here shows you how the data that our customers come to us with. You'll see the biggest circle there, 60% of our customers come with an Excel spreadsheet that has less than 100 data points in. A data point is one experiment, so all of the ingredients that are put in, all of the processing parameters, all of the test results from that experiment. So 100 or less experiments in an Excel spreadsheet. We have had a customer come to us with no data. They were wanting to go into a new area, and we helped them to plan out a series of 20 or so experiments to start with to give us enough data to get going. And then, we were able to help them be successful too. So you're not talking about needing a huge database before you come to us. Obviously, if you've got structured data, you've got it all digitalized, great, and we can use that and we can, pipe it into our system. But if you've got an Excel spreadsheet, then that's just fine too. In fact, we really recommend not doing a big data project to start. So if you spend 6 months, 12 months, or more sorting out your data, digitalizing it, putting it into a database before you start AI, then you're wasting time. You don't generate business value from the data management part of it. You generate the business value from starting to do AI. And if you start with 2 or 3 projects, small projects with, say, 30 data points, then what you do from that is you understand more about your data. You understand which is useful and which isn't useful for your AI projects. You also demonstrate value from AI, which then motivates you and other people to start taking data seriously in the future, to record everything properly. And it helps you to put together a good data strategy so that you can start scaling AI. So what's the most important thing you can do now with your data? You can, first of all, make sure all future data generated in your organization connects the inputs and the outputs. So in our world, the inputs are the formulation, the processing parameters, etc. And the outputs are final properties, whether that be Young's modulus or flammability. So make sure that you've got a sample ID for everything that you test and that that's connected to both inputs and outputs. And make sure you save all your data. So AI thrives on a really good diet of diverse data. If you put in bad results, you help the AI to learn what doesn't work. And then it can prevent you from doing what doesn't work in the future. So you want to save bad results as well as good and try and, save a good variety of data. Now, thinking about that data, make sure that you work with an AI platform that can capture all of your data. It's very rich. Here you can see a process diagram. I think it's for ABS plastic. On the left there, you can see the ingredients going in. Then there's a couple of processes, a new ingredient is added, and there's a final injection molding step. This is an interactive part of the platform that we provide. You can click on any of these boxes and see the properties of the ingredient, the parameters of the processing step, the properties of the final output. And you can see in the top right there that we can capture the molecules. So that's one of the ingredients in this. And we've typed in a string of letters and numbers that represent the molecular structure. What we then do is calculate other properties using that. You can see that from knowing what the molecular structure is, you automatically know the molecular weight, or you can automatically calculate the number of hydrogen bonds, for example. So that also gives you extra data. So let's move on to the AI workflow and think about what you do. And we've talked about data, that's where you start. And in the Citrine platform, you can drag and drop your data into the platform using an Excel spreadsheet. You have to format that spreadsheet to be labeled with your inputs and your outputs. But after you've done that, you just drag it into the platform. From there, I think it's 3 clicks, you get an AI model created automatically. So no code involved. It automatically creates an AI model from your data. It's a default model, and its defaults are based on us doing materials informatics for the last 12 years and having learnt what works and what doesn't. Now, on top of that, you're going to use your knowledge to make the AI model even better. So if you know that one property is related to another property, you can connect them and give the AI model that information. If you know, for example, that a ratio of certain ingredients is important, again, you can put that into the AI model. Then you can set constraints on the formulation. This is where you can put in your business nous. You can make sure that the formulations that are produced are practical, feasible, able to scale up. So, for example, if your stirring process can't go above 60 RPM, then you can set that as a constraint so that you don't get suggested formulations with a higher RPM. You can also set constraints about which ingredients can be used or raw materials. So, for example, you can create a different search space for the EU and the US, depending on the allowed raw materials in that region. Then finally, you set target properties, and this is multi-objectives. So you can say, I want to minimize this, maximize that, and be within this and this on this other property. And what it does is it runs the AI model over the search space. So it generates a list of formulations and it ranks them by their likelihood of success in the lab. So it predicts not only the properties, the target properties that you're interested in, and screens them based on your targets, but it also looks at the likelihood of success. So it estimates the uncertainty of its own predictions, and uses that uncertainty to predict whether or not what the formulation is a safe bet, and you can take it to the lab and definitely get the properties that you're looking for, or whether it's more of an exploratory experiment, something where you've got a low chance of getting really good results, for example. You're then there to guide and to be strategic and choose what to take to the lab. And getting to the lab and running experiments as quickly as possible is the key to getting success as quickly as possible. So you're going to take your experiments to the lab, run the experiments. The results on the first round, you're unlikely to meet all of your target properties, but what you will do is you will learn from those experiments. You take the data, you put it back into the data set that you're working on, you retrain the model using that data, it becomes more accurate, and it then suggests better candidates for you to take to the lab. So it's like a learning loop that reinforces itself. And if you're wondering, how does this reduce the number of experiments that you do to hit your target properties? It's this bit here. When you go to the lab doing trial and error using scientific intuition, and even if you do a design of experiment and you've got a grid of experiments, you don't know exactly what the chance of success of these experiments is. In design of experiment, all the experiments are equally likely to be successful or to fail. So it's this extra information that you get from calculating the uncertainty of your predictions that lets you be more strategic about what to take to the lab. And that is why we see between 50 and 80% fewer experiments to hit targets. Okay, so we've gone over the data, we've gone over the AI workflow. Now let's think about the human in the loop. In order to use small data, which is what we're in with materials and chemicals, we can't just use the data alone. We have to use the knowledge in the heads of the researchers. That's what really makes things happen. So what we need to do is to empower every scientist, engineer, even those that don't know how to code, people like me that never did that at university. We need to enable them to use the platform and the AI models. What this does is it cuts out the middleman. So if you work with a data scientist who uses the AI models, then there's going to be some confusion in communication. You know, you've got an extra step there. It also means that you can iterate more quickly. You can try out a new idea that you've had. And you've got more ownership. And when people feel more ownership, they're more likely to use it. The quote there is from a application engineer at one of our customers. He was so happy that although AI felt quite far away, that when he used the Citrine platform, he didn't need to use any programming skills. Now, you might be wondering why I've got the picture on the right. And this is actually to represent another of our customers who really got into using the platform because he really loved trying things out and running the model to see if it got better and looking for information from the models. He actually let known that he had used the Citrine platform on his mobile phone while sat in a jacuzzi on holiday. I'm not sure what his wife thought about that, but he was very happy that he could try out his idea. The other thing that we need to do is to make sure that scientists can trust the platform. Now, researchers don't like black boxes, right? They don't like something to just tell them the answer and they don't know what the reasoning is. So what we have done is make sure that we can display which factors are important for predicting a certain property. What this does is it means that researchers can sense check the model. You know, if it's using properties that don't make sense, then, something's gone wrong. But also it means that you can learn from the model. So sometimes, because we calculate all of those 127 different things about the chemicals used in the formulation, then sometimes something comes up where suddenly a researcher goes, "Oh, I didn't know that that was important for my property." But having looked at that, it totally makes sense. So scientists love this. It unlocks and shows them things that they haven't seen before. They really enjoy this interplay of using the AI to systematically go through things and speed things up, but also using it to uncover factors that they just didn't know were important. And now I'm going to hand over to my colleague Xavier Linn. He works directly with our customers and can show you on the platform how it all works.
All right, thanks, Hannah, and welcome everyone to the Citrine platform. In today's demo, I'll walk you through how to go from an Excel file to a set of candidate experiments generated by Citrine's AI, all in the few clicks of a mouse without needing to write a single line of code. What you're seeing now is a landing page for a project titled ABS, Mechanical Property and Cost Optimization. The focus of this project is to develop ABS plastics that are stronger and more cost-effective. In the Citrine platform, projects are collections of training sets, which are samples of your data corpus or your historical data. AI models, which is where you define how to predict specific properties that you're interested in terms of your domain knowledge and how to best make those predictions. There are then search spaces where we specify different sets of constraints in terms of how you want to design your materials. And finally, candidates, where we will combine your AI model with your search space to surface candidates that are optimizing specific targets. Below is an example workflow where we've configured a collection of assets to maximize the flexural modulus and impact strength while constraining on cost. The overall process starts with uploading your data from Excel and ends with reviewing AI suggested experiments. We'll go through this entire workflow and build it up step by step. But first, let's jump and take a quick look at the candidate experiments to see what they look like, and then we'll rewind and walk through how we got there. So candidate experiments on the Citrine platform are generated based on a set of optimization targets. We refer to these as objectives and constraints. In this example, we're maximizing flexural modulus, notched izod impact strength, and constraining on cost. During the optimization process, the Citrine platform evaluates hundreds of thousands of candidate experiments and then returns the top 100 that best balance exploiting known patterns in your historical data with exploring new promising areas. Each candidate is assigned a score between 0 and 1, which reflects how confident the platform is it will meet your objectives and constraints. A score of 1 means that the platform is very confident the candidate will hit the targets, while a score of 0 means the opposite. As part of selecting which candidates to take to the lab, we can review the candidates both in aggregate and individually. Right now, we're looking at the candidates in aggregate by visualizing the optimized properties related to one another. For example, here we have notched izod impact strength on the vertical axis and flexural modulus on the horizontal axis. Each of the data points in this plot represents a candidate that was surfaced by the AI. From the candidate details page, we can view the property predictions with uncertainty, as well as the data required to produce this candidate in the lab. So for example, here we have each of the properties that were included in our objectives and constraints. We can see the total composition of this candidate, both in terms of the individual ingredients and their weight percent of each, as well as label shares. So the idea on the Citrine platform is that we can assign labels to individual components to be able to use them as design space constraints and to use them as model inputs. So for example, here we can see, for example, that this candidate has used under the flame retardant label 3 different flame retardants. Going down, we can also see that we have other parameters that are included as part of this candidate. In producing an ABS plastic, there are several processing conditions that are required to make a plastic, and those are listed here. We also present featurized data. This is data that was computed in the AI model as these candidates were processed by the AI model For example, in our AI model, we have included molecular structure information pertaining to the raw materials, and we have then computed mean properties associated with raw materials, and we can see those calculated values here. And the idea here is that once we have selected a set of candidates to take to the lab, we're going to evaluate those results by running the experiments, and some of those experiments may perform poorly, while others may perform mediocre, while some may perform well. We'll then load the results back into the system so that the AI can learn from those outcomes. This workflow continues iteratively, with the AI model suggesting new candidate experiments that better satisfy the defined objectives and constraints. It does this by exploring a broader range of ingredient and processing combinations than traditional trial and error methods or techniques like design of experiments. All right, so at this point, you've seen what the AI can produce. Now let's talk through how we get from an Excel file to candidate experiments step by step. And from Data Manager, this is where I can view and manage all the data sets that belong to a given team. So I'll select the data engineering team, and this is where I can see both the raw and process data that is stored before being used in AI projects. Right now, I'm looking at the ABS polymers dataset, and I can select one of the materials that is included within this dataset to see how it's produced. So from this material details page, I can see the material identifier. So this material is named molded part 0. I can see a summary of the measured properties. And if I scroll down to the bottom, I can see what we call the material history visualization. So the way that data is stored on the Citrine platform is inside of Citrine's data model called GEMD. It stands for Graphical Expression of Materials Data. It is a data model that was specifically designed to capture all the context-rich information that goes into developing materials and has the flexibility to adapt to different data structures that arise through trying different things in the R&D process. So the way to interpret this graph is we can start left to right. So on the left-hand side of the graph, we begin the process flow where we're acquiring individual raw materials and feeding those into a powder pre-dry process with specified conditions and ratios of ingredient quantities and labels. For each of these raw materials, we can see associated physical properties. So for example, this specific raw material has molecular weight, density, price, and also a chemical structure string. And the way that we continue to read this is that we basically go from left to right, traversing through this graph until we reach the final produced material, in this case, which is molded part 0, which is produced by this injection molding process, and then we can see the properties that are included for this molded part. And these properties here are what we were looking at when we were examining the experiments that we had suggested, that had been suggested by the AI earlier. Okay, so the idea is that this is how we store your data on the platform. And the main way to get data onto your platform is by uploading Excel or CSV files. So from here, let's go ahead and take a look at how data needs to be formatted for easy upload to the Citrine platform. And I'm going to show you how to load your data. So I'm going to go back to Data Manager. And so within this data engineering team, I'm going to click on the Add New Data button. I've already created a data set for today called ABS polymers. I'm going to be writing into this existing data set. From here, I need to find my files on my local machine. I will then hit upload. I can optionally add a title and description in here if I find that helpful. I'll click upload, and then I'll move on to the next part where I begin ingesting the data. And so what's happening here is we're uploading the file to the system. We are then parsing the file, iterating through the rows and columns, and automatically building up those graphical structures for you for how your data is stored within the Citrine system. So this process typically takes anywhere between 5 and 10 minutes, depending on the size of your data. I've already loaded the data into this data set, so for the interest of time, I'm going to continue on to the next part of the process, which will be to navigate over to the project page where I can then now reference that data that I have loaded into a specific project. I will be using the existing project from before, the ABS mechanical property and cost optimization project. So the next part of this workflow that we see here is, we need to have a training set. The training set is essentially a data structure that lives in between the data set and the AI model, where you can create a training set from a combination of data sets. So for here, what I'll do is I'll create a new training set. And part of the training set is I need to give it a name, and I need to select the data sets that I want to pull from. I will be pulling from just the ABS polymers data set. And from here, I could immediately give this training set a name and then click on this Next and Generate button to begin the process of creating the training set and having it then ready for my AI model. But to add a little bit of detail here, we have the ability to create training sets where we subset the materials based on metadata tags. So in my data set, I've included some tags that denote the operator that produced each of the materials. So what I'll do here is I'll just select tags for operator Jane and operator Mark, and then I'll use that information to name my training set accordingly. So I'm going to say Mark and Jane ABS experiments. I'll hit the check mark to save the name. And then I can notice here that, after I've added these additional tags, the total number of samples that were being discovered from this query that I was forming went from 150 to 112. So as we're building out our query, we can get a sense of how much data is getting pulled in. So from here, I'm going to click on Next and Generate, and then I will begin the process of generating the training set. So in this step here, what's happening is we are taking the query that I've defined on the previous page. I'm going into the data sets that I've associated with this query, and I'm extracting out this information into a tabular form that the AI model consumes. This process of generating the training set can take up to 10 minutes, depending on the size of the data. It generally goes pretty quick, but in the interest of time, oh, look at that, it's already done. So this is the page for looking at your training set. There's a lot of neat things that you can do to visualize the data within the training set. For example, we have a multi-plot, we have a single plot. There's the ability to look at a distribution plot for outliers to understand, the distribution of your data. Very helpful for getting basic data visualization insights into your data. I will not spend a lot of time here in the interest of time. So what I'm going to do is, now that I have my training set created, I'm going to go back to the project page, and we will do the next step in the workflow, which is to create an AI model from our training set. Okay, so from here, I'm going to return back to the project page. Now that I have a training set created for this demo, I'm going to create a new workflow where I can start to combine my training set with an AI model, a search space, and a candidate generation. So for this, I'm going to create a new workflow. We also refer to this as a branch. I'll call this the ABS demo branch. I'll hit the check mark here. And from this point on, I can start assembling my assets. So I have a couple of training sets to choose from. I'm going to use the training set I just created that includes only Mark and Jane's ABS experiments. And the next part of this workflow is to select an AI model. What I'm going to do is I'm going to have the platform create a default AI model for me based on the training set that I'm pairing it with. So this process is creating a default AI model. The default AI model is the Citrine's platform's best guess as to what model it is that you want to build. We essentially throw the kitchen sink at the AI model, so we include all the data in your training set, and we assume sort of what are the properties that you want to predict. The intent with the default AI model is to give you a nice starting point to begin modifying its configuration according to your domain knowledge. The way to understand our AI models is that we take a graphical approach. So the root of this graph is what we call the training data. This is just a node in the graph that summarizes all of the different sort of descriptors or dimensions that are available in the data. And the way that this works is that as your data is fed into this node here, it flows through this model graph where these collections of nodes in the middle are essentially computing aggregate information about how your material is produced based on the upstream information. So in these models at the bottom here, this is where we're predicting the properties of our terminal materials, our ABS plastic materials, the endpoints in our process flow diagram, and we have the ability to configure for a given machine learning model what are the properties that we want to be included in a given model, and what are the inputs that we want to use into making those predictions. The possible inputs that are available to us are computed by looking at the upstream information. So we, for example, compute the total amount of ingredient fractions that are in each formulation, as well as mean properties of the raw materials and label fractions. So we're computing aggregate information of the process flow diagram, and then we can use that aggregate information as inputs into our machine learning models, where we want to be able to predict the various properties and specify their inputs. There's a lot of ways to incorporate domain knowledge into your model graph. For example, if there are sort of analytical relationships that you want to include, we have the ability to include custom formulas, where you can define a custom formula to compute a new value that you can use as an input. There's a lot of resources to help you get started with incorporating domain knowledge into your model. We have this Help Scout menu option at the bottom right-hand corner of the screen that allows you to look up articles on how to do certain activities within the Citrine platform. So for example, we have written articles here on understanding what the AI model is, how to work with it. We also have the ability to ask a AI bot questions about certain activities on the Citrine platform. So for example, how do I integrate domain knowledge into my AI model? I can ask this question and I'll get a response back on what are the types of activities that I can do to incorporate domain knowledge. But this is basically what the AI model is. It's where we define what are the machine learning models that we want to build, and for each of those machine learning models, what are the properties that we want to predict, and what are the inputs to predicting those properties. The way that this works is we will first build a default model, we'll then train this AI model, and from here, once the model is trained, it will then go into evaluation, where we apply a rigorous model evaluation workflow to understand the performance of the model. This process takes a little bit of time, so what I'm going to do from here is I'm going to jump over to the model I had created beforehand, and then we can look at the evaluation of the model. So for each of the machine learning models that we defined in each of the properties that we're predicting, we can see a summary of the performance of those models. We offer basic performance metrics like root mean squared error, non-dimensional model error, and R squared. We can look at further details for each of these models to understand how the model is making its predictions. So one of the common pain points with machine learning techniques is, it's a bit of a black box. You don't fully understand how the model is using the data to make its predictions. But the Citrine platform has provided a solution for that by incorporating feature importances into the model evaluation, where we can see for each model what were the most important features that had the most influence in explaining the variance of the output. So for example, in this model for predicting the tensile strength, we have realized here that based on the model training that the total fiber share in the flat formulation, in our formulation, is the most important feature. In addition to having ranked feature importances, we also provide feature impact plots, which tell you, sort of directionally how for each of the most important features, as you increase or decrease it, how it moves the property predictions. So there's a lot of ways to basically understand how the model is making its predictions. We also offer the capability to be able to run point predictions. So suppose you want to take an existing historical data point and slightly modify it to be able to see how its properties would change. So for example, here I can modify the original injection molding temperature for this historical data point called molded part 0 and run the prediction to see what the new values are. So this is the model page. This is one of the most interesting parts of the platform, where you can define your AI model, incorporate your domain knowledge, and then understand how the model is making its predictions. So the next part of this workflow is going to be creating a search space. So for that, I will go back to the branch page. So the idea with the search space is that This is where you specify the constraints for all of the things that you can control. So for example, here we're looking at the labels tab where we can set constraints on the amount of label share from each of our ingredients. We can also set constraints on the amounts of individual ingredients. So for example, under this fiber label, we have each of the different types of fiber components that are in our data, and then we can set constraints on them. The way that the default search space is created is that we will bound the constraints based on the values that we see in your training data as a way to give you a reasonable starting point for further modifying to your needs. So one example for this could be, suppose that I'm trying to optimize the mechanical properties of an ABS plastic, but I have been informed by my customer there's a certain flame retardant that I can't use. Suppose I can't use, the customer said, based on regulatory reasons, we cannot use octa BDE, so I'm going to mark that as exclude, and we cannot use hexabromocyclododecane, and I can mark those as exclude. And then the idea here is that when we are using our AI model to explore the search space, that as we're exploring the search space, we will need to make sure that candidates that are pulled from the search space to be scored and presented to you need to adhere to these constraints. So we're sort of guiding the model to explore the regions of the design space that we think are physically sensible and maybe particularly interesting or influenced by certain design constraints that are imposed by people who are needing these materials. So from here, what I'll do is I'll give the search space a name, and I'll just say reduced flame retardant, and I'll save the name. I'll then move on to the validation step. So the idea here is that when you define your search space, we will make sure that it's valid and that you haven't set any constraints that would not allow us to draw valid samples. So this process is validating. Once this process is complete, we can then move on to the next part of the workflow, which would be to pair a candidate execution with the search space. And that actually brings us full circle to what we've covered so far. So previously, we dove into candidates to see what that looks like, and essentially we have come full circle where we have uploaded our Excel data file, we've created our training set with a subset of the historical data containing only Mark and Jane's experiments. We've then created a default AI model, and from that default AI model, we have created a search space, and we have modified the search space from the default configuration to exclude a couple of flame retardants for a hypothetical design problem. And that is basically everything I wanted to show. So I think at this point, Hannah, I can hand it over to you, and I would be more than happy to answer questions at the end. I know that we covered a lot of ground, so if anything isn't clear or you have further questions about how things work, please let me know.
Thanks, Xavi. So to finish off, you might want to learn a bit more about how to get started with AI. What we've done is we've put together a white paper synthesizing all of the things that we've learned over the years about how to get started. So which projects to start with, how to get your team enthusiastic about it, and so on. So you might want to download that. Also on the website, we have a resources section with other white papers, case studies, and webinars that you can access. So in summary, materials and chemicals informatics is happening now. It's not the future. Companies are already using it, and those that don't start using it in the next couple of years will be outcompete. Data isn't the issue that you might think it is. You need a small, diverse data set to start with. You can see up to 50 to 80% decrease in the number of experiments that you need to do to reach your targets. And you don't need any data science background or code to be able to use AI. The platform is easy to adopt. We've got a decade of experience on how to roll it out across an enterprise. So please get in touch. email us, request a demo, we can help.